All right, good morning, calculus. So please bear with me. I forgot my tripod, so I'm going to try to do this while I'm holding my phone and still try to teach you about rates of change in tangent lines. So right now I'm dropping off Vinny for his first day of preschool, but still want to make sure that you are caught up on everything you need to know about calculus. So you should already have these notes from the sub, and these two videos that are referenced here, I've included those links to the classroom as well, so you can check those out so you know what we're talking about. So in those videos, you saw that there's an object dropped from an initial height, h naught. In this case, it's from this dam up here at 594 feet. So what we want to do, we're going to use this position function to model the height in feet after the object has fallen for so many seconds. So what we're going to do is try to figure out what the position function, based on this model, is for our ball. Now here we have our dam is at 594 feet tall. So what we're going to do is take s of t and set that equal to negative 16 t squared plus 594. All right, so the next thing we're going to look at is the question we want to know is how fast is the ball moving? Now we have some tools that we can use to describe how fast this ball would be moving. And in our case, what we have is this average velocity right here. That's what we have so far. And it can be found by using this formula. The numerator is the change in distance. The denominator is the change in time. So what we're going to do is find the basketball's average velocity for the first 3 seconds of flight. So the first 3 seconds of flight is going to be from 0 to 3. So we'll go ahead and plug that in. So we'll take our change in distance. So that means we're going to have to plug in 3 for where the ball is located at 3 seconds. So that's going to be s of 3 minus s of 0 all over 3 minus 0. What should this remind you of? I want you to think about it. Change in height over change in time, change in y over in change in x. Yes. This is a slope formula for the slope between 2 points. All right, I want to switch to a new pen here. So here we have the location, the height at 3 seconds is 450. The height at 0 seconds is at 594, where we're starting. Then we divide by the amount of change in time. When we simplify that expression, we get to negative 48 feet per second. So that's the average velocity over 3 seconds. But what we would like to do is we really want to figure out what's happening at the instant t equals 3 seconds. What's happening at that very moment in time? Well, the only tool we have is the average velocity, so we're going to try to use the average velocity as best we can. What we'd like to do, let's shorten up this change in time. If we're looking at, if negative 48 feet per second is the average rate for 3 seconds, well, what if we shorten up that time to just 1 second? So let's go ahead and do that. So this would mean we have s of 3 minus s of 2 over 3 minus 2. And then that's going to give us, again, 450 minus 530 over 1, which is negative 80 feet per second. But again, that's only the first, or just from the second to the third second, from 2 to 3 seconds, and that's only a change in 1 second. Still, there's time elapsing. We want to know what's happening in exactly 3 seconds, so we're still going to have to do something different. So we're going to still have to find what this basketball's velocity at the instant 3 seconds is, and the only thing we can use is this idea here, average velocity. So let's go ahead and try plugging that in. So we've got s of 3, and of course we want to know what's happening at instantly 3 seconds. So that means the change in height, there's no change in height because I want to know what's happening at this moment. There's no change in height. And also, since we're looking at a moment, there's no change in time either. So we end up getting 0 over 0. We get an indeterminate form. How in the world are we supposed to figure out what's happening at instantly 3 seconds if the tools we have won't only give us the indeterminate form? We're going to have to do a little more investigation. So let's see what's happening from 2.5 to 3 seconds. We're still going to shorten up that time span to just a half a second. And it looks like we're getting closer to something. First, we started off at negative 48 feet per second for the average rate of change over 3 seconds. Over 1 second, from 2 to 3 seconds, it was negative 80 feet per second. Now we're at negative 88 feet per second. So it looks like we're getting somewhere. So that was over half a second, from 2.5 to 3. Let's move over here to 2.9 to 3, a tenth of a second. So if we allow the rate of allow the time to elapse for just a tenth of a second and calculate the average velocity over that tenth of a second, we get negative 94.4 feet per second. So it looks like we're still getting closer to the value that we want, and we want to get even closer. So let's look at the average velocity between 2.99 and 3 seconds. Even closer. Now we're at negative 95.84 feet per second. It's like we're approaching something. And we move over here. The average velocity between 2.999 and 3 seconds. Now we're at negative 95.984. So the question is this. What is the basketball's velocity approaching at t equals 3 seconds? Well, that value that we just keep getting closer and closer and closer to is negative 96 feet. It's a little blurry there, sorry. Per second. So what we did is evaluate a limit numerically. We'd like to have a better process for that so we don't have to go to a table or a table of values every time to figure out what this instantaneous velocity is. All right, so what we're going to do is use a secant line, or the average rate of change of a function, to figure out what the instantaneous rate of change is for this instantaneous velocity is for this basketball. So we're going to start off with, we have some curve here, and there's 2 points on this curve, and I'm going to label each of these points. This first curve is the point A, comma, f of A. The second comma has an x value of b, and a height of f of b, because f is a function that is describing this curve. If I want to find the average rate of change, I'm simply using slope between 2 points. That's all this is. The average rate of change of a function is slope. So let's figure out what that average rate of change would be. If I look at, say, a function like this, x cubed minus x over the interval 1 to 3, I would use f of b minus f of a all over b minus a, the average rate of change formula, and calculate that in this way. I would find f of 3 minus f of 1, the initial and the final, over the interval 3 to 1. I'm sorry, 1 to 3, and simplify. F of 3, when I plug it into my function, I get 24. F of 1, I get 0, and the interval is 2, which simplifies to 12. It's very important to understand what this means. The phrase I would use is the average rate of change of the function is 12. What that means graphically is that if I look at all these little slopes at any point along this curve, because you've never been asked what the slope of a curve is, it doesn't make sense. There's an infinite number of tangent lines. So we'll use a secant line to describe the average of all these infinite number of little slopes. The average of all these slopes is 12. That's what we're looking for. So here's the payoff. Let's say we're starting at this point. I want to know what's happening instantaneously at this moment. Well, the only tool we have right now is being able to find average velocity using 2 points. I would like to know what is the slope of the line using a single point. So let's consider this. This is the point A, f of A. A is what we want. But let's say I just scoot down the curve a little bit more. And that little bit more is called h. That h is a distance of x, that's just a little bit more. So what I call that a plus h. So it's the x value I start with plus a little bit more. And what I plug in is the x value I start with plus a little bit more. So technically, they are 2 different points. Well, what h allows me to do is that I can try to shrink h. I'm going to try to shrink h so that it comes back to the point that I want. that means this point is going to slide down the curve so that it behaves more like a tangent line. Well, that being said, let's go ahead and try our formula. So we have f of a plus h, the second point where I'm ending up, minus f of, f of a. And this is all over a plus h minus a. Now let's simplify this. What happens is, well, the a's cancel out, and all I'm left with is f of a plus a little bit more, a plus h, minus f of a. That's all over just h. Now, I want h to behave like nothing. I want it to behave like it's 0. But I can't plug in 0 here. But we have a calculus tool that allows h to become 0. So what we will do is take the limit of this expression as h approaches 0. And what this does is this tells us the slope of a line at a single point. Put a star next to this and memorize this. All right, so we're going to skip ahead in the notes a little bit down to example 3. Completed notes will be posted, and I'll surely discuss a lot of these things in class on Monday, the next block date that I see you. So what we're going to do is find the slope of the curve f of x equals x squared at a particular point. So we know what x squared looks like. X squared looks something like this. We've got just a regular old parabola, and then we're looking at this and this. Look at my crude example. And then 2, 4 could be located here. So this could be 2, this could be 4. Here's the point. So I'm not looking at the slope of a secant line. I'm actually looking at what is the slope of the curve at that moment. So there's a tangent line that touches the curve only once. I want to find the slope of that line, but using only one point. So here's what we're going to do. We're going to take the slope, and this is called the difference quotient. Take the limit as h approaches 0 of f of a plus h minus f of a all over h. Now in our case, we have the limit as h approaches 0. In our case, a is 2, and f of a plus h is 4. So here we have, I'm sorry, that's the f of a, and I'm sorry, not f of a plus h. I apologize, that's just f of a. So f of a plus h, we don't know what f of a plus h is yet. We are going to plug in a value of 2 since that's 8. So we have 2 plus h, then minus f of a, which is just 4. And that's all over h. Now, we're going to figure out, well, what does this formula do for us? F of 2 plus h. I'm going to take 2 plus h and plug it in wherever I see an x, because this is the function f. Our function f is x squared. So what this will become is the limit as h approaches 0 of 2 plus h squared minus 4 all over h. We continue this up here. So we can't evaluate the limit yet, but we can simplify. So we end up getting 4 plus, and then this would be 4h plus h squared minus 4 all over h. Now the goal here is that you will be able to cancel things out. So this is just evaluating a limit. Still can't plug in h? Well, look at that. 4 minus 4 is 0. And everything that's left behind has an h in the numerator, so I can cancel out a factor of h from everything I see. So what I'm left with is the limit as h approaches 0 of 4 plus h. So what I have found when I evaluate this limit is that the slope of the curve of x squared at this point 2, 4 is 4. Something else you're going to have to find often is the equation of a tangent line. We will use that a lot this year. For right now, we just want to be able to find it. We already know that the slope from example 3 is 4. So we already know that. And we know that we have the point 2, 4. So what we're going to do is use point slope form. Y minus y1 equals m times x minus x1 to easily write the equation of the line, and we can just leave it like that. Point slope form is your best friend this year. So we've got y minus 4 equals 4 times x minus 2, and there is the equation of said tangent line at the point 2, 4. All right, so back to the basketball example. We have the function that describes the basketball's position height over time, and we're going to find the slope of the curve at x equals 3. That means we're going to find the instantaneous velocity or instantaneous slope at time t equals 3. So let's go ahead and get this going. All right, so we're going to start off with our limits as h approaches 0 of f of a plus h minus f of a all over h. And when we plug in our values, we will get the limit as h approaches 0 of, first, a plus h. So we get negative 16 times a plus h squared plus 594 minus, let me cut this off here, negative, parentheses, negative 16a squared plus 594. And that's, oops, all over h. All right, so what I can do now is plug in a for all of those, and I already know that that is 3. So what we'll do here is the limit as h approaches 0 of negative 16 times 3 plus h squared plus 594 minus negative 16 times 3 squared plus 594. And that's all over h. And then we can start simplifying from there. So we have the limit as h approaches 0 of negative 16 times 9 plus, let's see, so it'd be 3 squared plus, let's see, 6h plus h squared plus 594 minus, let's see, what do we have here? 3 squared, that'd be 916. So you have negative 144 plus 594. All over h. And we just start simplifying. So here we can already see that we've got plus 144 and minus 594. I can start canceling some things out. So we'll cross out the 594s. And it looks like I've got 16 times 9, so that's going to be another negative 144 here. So negative 144. And then I have negative 16 times 6, so that's going to be negative 96h, and then negative 16h squared. So let's go ahead and clean this up. 144s cancel as well. So it looks like we're left with the limit as h approaches 0 of negative 96h minus 16h squared. Everything else canceled, so it's all over h. And what happens here is I can cancel out h's, and then I'm left with the limit as h approaches 0 of negative 96 minus 16h, and that limit, this would go to 0 as we evaluate the limit, so all that is left over is negative 96. Negative 96 feet per second, and that, folks, is what we predicted numerically all along.